Okay, so we were doing rigid body analysis and we started with rigid body planar kinematics. So in today's class, we will continue with the same topic and we will go further in that topic. And the specific topic for today's class, it is general plane motion. And in general plane motion, today we will study the relative motion analysis. Okay, so to understand the general plane motion, if you remember in last class we discussed that general plane motion means that it is basically combination of translation as well as rotation. Let's say we have a rigid body and at any instantaneous time or at any random time t, it moves from some other place to this current position. This is like the current position. So at time t, this object has reached to this current position. Now, after a certain time, maybe after some instantaneous time dt, the object moved from this current position to this new position. So means at time t, the initial position was here, and now after time t plus dt, the new position is here. So as I have told you, in general plane motion, we are having a combination of two different types of motion. One is just the simple translation, and the other one is basically the rotation. So you can see initially the object, when it was at this initial position, it was having different rotation. So now after some time, means at time t plus dt, the position as well as the orientation of this object is changed. Now to analyze that general plane motion, let us consider any 2 points, that is point A and point B on this rigid body. So at time t, both these points were having some specific position which we marked over here. Now let's say the object moved from here by exhibiting a general plane motion, means that motion can be clockwise or it can be even anti-clockwise, right? So let's say the object moved from this position to this new position by exhibiting general plane motion, means having rotation, having translation as well as rotation. So the object at this new place, it is having different position as well as different orientation. Now let's say if I want to find out the position of that point A with respect to the previous position point A. So the new position means initially when it was point A at this location, let it be called as point A, and when it moves to new position, let it be A prime. And initially the second point, which was point B, when it moved to new position, let it be B prime. So if you want to find out the position of this A prime with respect to A, so what we can do, we can use simply a position vector, right? So the position vector R, that will simply show the position of A prime with respect to origin A, right? Similarly, the position of B prime can be determined by using another position vector. Let's say RB, let it be RA and let it be RB. So whereas RB is the position vector that is showing the position of B prime with respect to B. And if we want to find out the position of this point B with respect to A, so the position vector in this case, it may be RB by A, right? And in this case, it will be RB dash by A dash. Okay. So as I have told you that I have represented this position with RA, but as I have told you initially that during an instant or during instantaneous time or during a very short period of time, the position vector again it will be instantaneous, or we can represent it by this differential term. So that's why we have represented over here by dra and drb. Okay, so as I have told you, the general plane motion, it is basically a combination of translation plus rotation. So initially when the object was here, so let's first consider translation. So it moves maybe by a straight line exhibiting a translation as shown over here. So the path followed by point A and the path followed by point B, both will be almost identical because it is translation, and the relative position of point B with respect to A, it was RB by A, it will remain the same, because we know that in translation the relative velocity of both points it remains same. As you can see over here. Okay, now after exhibiting, let's imagine that it's exhibiting the translation. Let's say that during this time it also rotated. Now for rotation we need some fixed origin. For example, if this is the object, if it has to rotate, if this object has to rotate, so for this rotation we need some fixed point. That fixed point may be over here, that may be over here, about which the object can rotate. So let's say in this case the fixed point is this point A, this one or this one, right? So means if this is a fixed point, or about this fixed point, if the rotation has to take place, or if this rigid body has to rotate, so the point A will remain in this in this location, means at this place on the object, right? Means its position will not be changed. However, the remaining points on this rigid body, it will be changed, or it will rotate around this point. This point it can translate, but it will remain on the same location on this object, right? Means it will not rotate, it will remain in the same place. Okay, so now let's say initially we consider only translation, let's also consider the rotation. So definitely rotation will be about a fixed point, or it will be about a fixed axis that passes through that certain point. So now let's imagine that rotation. The rotation takes place about that fixed point A or A dash, and during this the rotation takes place like this, and it reached the point B, move to this point B dash. So now to find out the position vector of this point B dash, we can have this new position vector. Okay, now the displacement that it cover from this position till this one, since it takes place during that instantaneous time dt, so it can be given as drb by a, right? And if I connect this point B, initial point B, is when point B was here, if I want to find out the position B dash with respect to this B, so I need a position vector like this, which I have shown over here, that is drb. So by using vector addition rule, what we can write, that drb is equal to this dra plus drb by a, right? So we can write it from this diagram. So now what happened, this plane has translated and as well as it rotated. So means we had a general plane motion, and by exhibiting or by analyzing it, we get this equation. Okay, so if we take time derivative of this equation, so what we will get from here, we get velocity of position B or point B. This will give us velocity of point A, and this one will give us the relative velocity of point B with respect to point A. Okay, so this means if we remove this portion, so what we will be having, we will be having VB is equal to VA. This means if the object move in a straight line, if object moves in a straight line, so those 2 points, that is A and B, will be having same velocity. So this means this portion is basically showing translation. Okay, but if it is not moving in a straight line, if it is exhibiting general plane motion, then B will not be equal to VA. There will be an additional term that will incorporate the rotation in this equation, right? So this VB, which is exhibiting, which is a combination of rotation and translation, that should be equal to VA plus VB by A. This is the relative velocity of point B with respect to A in a rigid body. Okay, so I have shown this thing over here, right? And this is the same diagram which I have shown. So means if this object B or this rigid body, if it rotates, so this point B move from here to B dash, so this means it is exhibiting rotation like this. So the angular velocity can be given like this, and angular acceleration can be given like this. Okay, now VB is equal to VA and VB by A. This is basically showing their rotation. We move this one to side. This portion is basically showing rotation of point B while keeping A as origin, and we know that the relationship between linear velocity and angular velocity can be given as omega cross r, right? And r is basically position vector, so we can write this one as omega angular velocity vector into cross product with the position vector, right? So by putting this one over here in this equation, over here, instead of this one, if we put this value, so we get this equation. Okay, so if we move back again to the previous one, this equation, and we take one time derivative of this equation, so we get the velocity, the equation for linear velocity of point B. Now let's say we have the same equation again. We have the same equation again, and we will in this time we will take double derivative with respect to time. So when you take double derivative, and we know that the double derivative of displacement vector will give us acceleration. So from here we get acceleration of point B, here acceleration of point A, and here basically acceleration of point B with respect to A. So AB will be equal to AA if it is only rotating, but here we are having the sorry, AB will be equal to AA if it is only having translation. But here we are having general plane motion, so to incorporate rotation we have this second term. And again, similar like the relationship between linear velocity and angular velocity, we are also having relationship between angular acceleration and linear acceleration, which we discuss or you would be derived in our previous classes. So this is basically AB by A is equal to alpha cross or B by A. Alpha is the angular acceleration, this is basically the position vector, and minus omega square RB by A. So this one basically showing the radial component, and this one is showing basically the normal component. This one is showing tangential, and this one is showing the normal component of acceleration. If you go through the previous lecture, you will remember that you will see that we have done this equation, or we have discussed this equation over there. Okay, so by putting these values over here in this equation, we get this new equation, right? So what does this equation show? This equation shows the acceleration of point B when the rigid body is exhibiting a general plane motion, when it is having both rotation as well as translation. Okay, so these two equations can be written for any two arbitrary points. Means but the one thing that we remember, that on any rigid body, if we are having any two arbitrary points, point 1 and 2, or point A and B, so we can write these two equations which we just derived. but we must keep this thing in mind that these 2 points must belong to the same rigid body, and if that rigid body is undergoing a general plane motion. But we remember that for using these two equations, we must select some reference point. So in this case, the reference point that we select, it was basically A. So to find out the position of point B, what we did, we had a position vector starting from A towards B, right? And we get these two equations, right? If we change the position of this origin, we keep point B as origin and find out the position of A with respect to this one, so that position vector will become like this, right? And in this case, instead of VB over here, we will be having equation VA, and here we will be having VB, right? And this cross product, it will be RA by B, right? And omega AB RBA is same. Similarly, it will be EA, and same way the equation will be changed. So now if we consider point B, so if we consider point B, the as I have told you, the equation will be changed like this: VA is equal to VB plus VBA, VB plus VBAR, VB plus omega AB RBA is same into RAB. It's again the position vector that is showing the position of point A with respect to B. In previous case, it was B to A. For this one, it's B now. And similarly, we will be having the case for acceleration. Okay. So from here, we can at least write these two equations, and these equations definitely will enable us to find the linear velocity and linear acceleration for any specific point in case of a rigid body exhibiting planar motion. Okay, now let's see if we are having 2 points, and one of the points, that is, for example, point A, if it belongs to more than one rigid body. For example, over here, we are having this rigid body, and if you have 2 points, so we can write these two equations for it. But if you have point that belongs to more than one rigid body is over here, one rigid body is over here, and that can be like, for example, in the case of joints, for example, 2 rigid bodies are joined at this point, right? So in this figure, that point A, it belongs to rigid body AB as well as rigid body AC. So in this case, the linear velocity and linear acceleration can also be written as by incorporating that AC. Over here, we have VA, AA, and that is with respect to point B. With respect to point B. So we can, if you want to write it for AC, for the second rigid body, the velocity and acceleration of point A, we can write it like this. Means replace this VB by VC, AB by AC, and position vector A slash B by RA slash C. Right? So this is in a case if single point belongs to more than one rigid body. And same is the case for acceleration. So you need to remember these equations. These equations are very important, and these equations will be used in coming problems. Okay. So now to understand this concept, let's have an example. In this example, this color C, it slides. Slide like this and like this. Okay. Now this object, this link AB, it only rotate like this, right? But this link it moves, this end is moved with this one, and it also rotates. So this one is having both motion. This link BC, it is having general plane motion, that is translation plus rotation. But if we consider like this, that the motion is in this direction of this link, if it is in this direction, if it moves like this, the rotation will be in this direction. The rotation can be like this, right? And definitely the rotation over here, it will be in this direction. So what they are asking, if color C slides with linear velocity and acceleration as shown, with this linear velocity and linear acceleration, determine the angular velocity and angular acceleration of rod BC. We need to find out the angular velocity and angular acceleration of this rod BC. Let me remove. We need to find out the angular velocity and angular acceleration of this link or this rod BC. Okay. So let's write down equation for this point C. Okay. So this rod BC, it is basically having general plane motion. It is having general plane motion, that is combination of translation plus rotation. So let's say if I write equation, if I try to find out the velocity of point C, so that will be velocity of point C is basically equal to the translation plus rotation of that rigid body or that rod or that link. Similarly, the acceleration again, it can be written like this, and it's the same equation which I just discussed. This one, or let it be just this equation, right? So we are writing it for point B and for this point, but in the problem we are having point C. The relationship is between point C and B, not A and B. Okay, so we wrote these two equations. Okay, but in this equation we are having two unknowns. What they are asking for: determine the angular velocity and angular velocity and acceleration of rod BC. So this means alpha omega BC and alpha BC is unknown. In this equation, this is unknown, this is also unknown, right? We can find out this one, we can find out this one, but do we have VC? Yes, we have VC. Do we have AC? Yes, we have AC. We don't have VB and we don't have AB. अगर हमारे पास if we had that velocity of point B and linear velocity of linear acceleration of point B, this problem would have been solved. So indirectly we need to do something for it. So now let us consider, okay, let's consider this link AB. It is having only rotation, right? If we consider only this link, it is having only translation. So let's consider rod AB. This rod AB, it is having only rotation. So means it is rotating like this. Okay. At this point, if you want to find out its velocity, so the direction of velocity can be given as tangent. And it is always perpendicular to the radius. Or in other words, the velocity of point B, it is perpendicular to the position vector RBA, right? And it is having only rotation. So in case of rotation, the direction of velocity can mean the linear velocity relationship can be given as omega cross R. So omega, the linear velocity of point B, that is equal to the angular velocity into the position vector. So the angular velocity of AB is given by omega AB, right? And the position vector from here till here, it can be given as RB by A. So RB by A, that will be combination of x distance and y distance. That x distance and y distance. So how we can find out that x distance and that y distance? Do we have that angle? Yes, we have angle over here. Do we have this distance? Yes. So this one will become 0.6 cos of 60, and this one will become 0.6 sine of 60 degree, right? If we have this x distance, that one will become a negative x direction. So that will be with negative sign, and this is going upward. So this will be with the positive side. So RB by A can be identified. So this is basically the position vector, right? Okay. So omega AB is as it is, RB by A. Instead of RB by A, we have put it the values, these values. Okay. Now, as I have told you, the rotation is like this. It is within XY plane. So definitely the direction will be perpendicular to the plane by using right hand rule. And this direction will be in Z direction. This is in Z. And the unit vector along Z is K. So that's why with omega AB, if you want to write it in vector form, so that will be magnitude into the unit vector, which is K, and it is along Z direction. And instead of RBA, you can write down this position vector. So when you solve it, what you will get this equation. That is VB in vector form. That will be equal to this one. Okay. Now let's consider the general plane motion of BC. General plane motion of BC. So it is having translation as well as rotation. So the velocity of point C over here, that is equal to, again, we discussed this one even in the previous slide. This is the same as this one, same equation as this one. So let's write it again. As VC is equal to VB, that is linear plus rotation, or translation plus rotation. Okay, so now we have value for VB. So instead of VB, we can put this equation. We can put this equation. When you put this equation, VC will become equal to this VP, and then we have omega BC, and then RCB. Okay, how we can find out this RCB? RCB. So for this, we will need this X value and this Y value, right? And we have this 0.4. If you have this 0.4, we need this angle. This is 45 degree from here. So by calculation, this one will become 0.4 cos of 45. This one will become 0.4 sine of 45, right? So when you do so, you will get the value of RCB. Okay. So the value of RC have been identified. The value of RCB has been identified from here. Okay, and again, as I have told you, that the direction of angular acceleration, angular velocity, it will be along K, or it will be along Z axis. So we have put it this in vector form, also the position vector. So these are all the value. When you solve this problem, or when you arrange this one, let take all I component on one side and the j component on the other side, right? Okay, so this one is I, this one is j. Multiply this one inside, and you remember that how to do that cross multiplication, or multiplication in case of cross product. So when you do so, this is the final arranged form: 0.520 omega AB minus 0.283 omega BC, and this is the I component, and these are the values for j component, right? Okay, so what is this? This is VC, and in question it is given that VC is equal to 2 meter per second. This is basically the magnitude. And what about direction? Since the rotation is like this, so it can be possible only if this point C move towards right. So the direction is along x-axis, and it is along positive x-axis, and the unit vector along x-axis is I. So that's why instead of VC, we can write this 2I. So that's why I have put it equal to 2I. Now compare I component with I. Put I component equal to I component on the right side, and j component equal to j component on the right side, which is 0. When you do so, what you will get, when you do so and when you solve it like this. Okay, so in this now we are having two equations and two unknowns, right? So when you solve it, what you will get the value of omega AB and omega BC. So when one of the unknown, which was the angular velocity of rod BC, has been identified, which is omega BC. Now we need to work out for the angular acceleration of rod BC. Okay, so we know that for rod AB rotation, the equation is changed. It is not as simple as velocity equation. It is like this one, right? This is relationship between linear acceleration and angular acceleration. The angular acceleration is having tangential and normal component. Okay, so for rod BC, the linear acceleration and its relationship with angular acceleration can be given by this equation, right? And we know that the if you want to write down it in vector form or in component form, so angular acceleration AB, it is having direction along k direction, along z axis. So I have write it along its unit vector, or I have write it in form of its scalar component, and the direction, magnitude and direction is along k, and RB by A, which we already identified in the previous part. So we can write this value. Okay, and we already know the value of omega AB. So omega AB values have been directly put it over here, and we already know the position vector RB by A, which we already identified over here. Put it over here. Okay, so when you solve it, what you will get omega B is equal to this plus this. Now again, the acceleration is along x-axis because this component is moving along x-axis, and since as per given orientation, if the rotation is like this, so object has to move in this direction. This means the acceleration is also in this direction. So but this is just the magnitude. To show it in vector form, we need direction, and direction is along y-axis. So instead of AB, what we can put it as tan I. So compare or equate I with I, means left side I with right side I, and left side J with the right side J. When you do so, when you do this thing, what you will get? You will get this equation, right? And by doing this one, you will get, now in this one we are having two unknowns, and we are having two equations. One equation is this one, and one equation is this one, right? Okay, well, I have made a small mistake. Over here, the direction have been shown that velocity in this direction, but acceleration is in the reverse direction. It is in the opposite direction. So this was just a mistake. So instead of positive, I told you that we need to put it positive, but instead we need to put this, that acceleration in negative direction. That is minus tan I, not plus tan I, because direction is opposite. It is against x direction. Okay, that's why we have put it as minus tan I. So when you solve it, what we will get? We will get angular acceleration of length AB and angular acceleration of length BC, or rod BC, and that was the requirement. We identified the angular velocity and the angular acceleration of rod BC. Okay, so here we have an example from your book, that is example 16.6. What they are basically showing, the link shown in figure 1613A. The example is from R.C. Hibbeler book. Figure 1613A is guided by two blocks at A and B. This is block A, and this is block B, which moves in the fixed slot. Means this one can move up and down, and this one can move left and right. So if the movement over here is downward, so this means this movement, or the movement within this slot, it should be in the right side, means the movement of B should be on the right side. If the velocity of A is 2 meters per second downward, determine the velocity of B at an instant theta is equal to 45 degree. Okay, the angle is given over here. This angle, it is 45. Means velocity, this is in this direction downward, so this should be right. Okay, and they are saying this is 45 degree. Okay. What they are asking for? They are asking for velocity of B. So we can write similarly as we have done in the previous case, the general plane motion. We are interested in finding the velocity of B. So VB, definitely it will be combination of VA plus the rotation part. So VB is equal to VA plus the rotation part, which is omega into the position vector. So the position vector, okay, let's see. This motion is downward, this one is on the right side. So rotation is like this, and let's say this is X and this is Y. So if we are having counterclockwise direction, so according to right hand rule, the thumb will give us direction perpendicular to the plane, and it will be plus X, right? So omega will be the direction of omega. It will be along the Z direction with the unit vector K, and it should be positive. So with omega, if you want to write it down in terms of magnitude and unit vector, so it should be K with a plus sign. And VA is downward. So this means it is in downward direction with the unit vector J and with the negative sign. RB by A, we need to find out this thing. RB by A. Okay, this was the position. And what we are given with? We are given with this 0.2. And we need to find out this value and this value. So if we do so, what we can get? We can find out this RB by A. Position of point B with respect to point A. Right? So we are starting with this one. We need this distance. Okay. We need this distance and we need this distance. So how we can find out this distance and the other one, the distance over here? It's very much simple. This is 0.2 and this is 45. If this is 45, this means this is also 45. But let it be like this one. So this one is 0.2 cos of 45 and this is 0.2 sine of 45. So we are having this x component and y component. One is along I and one is along J, right? So if you're moving from point A to point B, the value along x-axis should be positive and the value along y-axis it should be negative. So the position vector RB by A, it is 0.2 sine 45I, and the one along J is 0.2 cos of 45J. So by doing the necessary multiplication or by finding the necessary product, we get this equation. So in this we are having two J components and one I component. So again, equate the I component of left side with the right side and J component of left side with the right side. When you do so, you will get VB I is equal to 0.2 omega cos 45 I will be cancelled out and you get VB is equal to 0.2 omega cos 45, right? And here we don't have any J component. So this J, that is 0. Minus 2 plus 0.2 omega sine 45, it will be equal to 0. When you solve it, what you will get? You will get the value of omega, which is 14.1 radian per second, and you will also get the linear velocity of point B, which is 2 meter per second. So this is basically an example from your book, R.C. Hibbler. So you can also go through the other related example in your book. Okay, again, it's just a brainstorming exercise for you people. What you need to do, you need to solve it. And once you get your answer, you need to compare with these given options and you need to select the option that closely resemble your answer. Okay, so now let's move towards the second portion of our today's class, that is basically general plane motion. And in general plane motion, what we are interested in finding the instantaneous center of zero velocity. Now, what is instantaneous center of zero velocity? Let's understand it. Okay, Let us consider we are having a rigid body that is exhibiting a general plane motion. For example, we have this body, it is exhibiting a general plane motion. Now let's imagine, maybe let's consider this as a fixed point, means the fixed point on the rigid body. The rigid body translate as well as rotate, and let's say the rotation which we can consist, means if a rigid body is rotating, so it can have angular velocity, also angular acceleration. So it is given by omega and alpha, and the directions are also shown. Let's say we are having 2 points, let point A be fixed and point B, it can rotate or it can move. So if we want to find out, means for a rotation, if you want to find out the direction of velocity of point B, so definitely it will be perpendicular to the position vector RB by A. What is RB by A? This is the position vector. This is basically showing the position of P with respect to the origin A, right? So for general plane motion, if you want to find out the velocity of V, that will be the combination of translation plus rotation. Let's say, suppose at any instant, if this VA becomes 0, means we have translation plus rotation. This is VA and this is omega. If this VA becomes 0, so this means this portion is cancelled. What we are left with? We are left with only rotation. If VA becomes 0, so this means that the velocity that will be only equal to the rotation part. So at this instant, then VB will be equal to omega RB by A. We will not be having any translation, we will be having only rotation. So if we are having only rotation, what we will get? The velocity of point B the linear velocity of point B, definitely it can be given as the angular velocity and its cross product with the position vector, right? And the position vector, since the fixed point is A and we want to find out the velocity of point B, so it will be cross product of omega with the position vector from B to A, that is RB by A. Similarly, if you want to consider any other point, that is point C, and if you want to find out the linear velocity of point C, so that will be the cross product of omega and the position vector from C to A, which is RC by A. And similarly, if you want to find out the linear velocity of point D, it can be given like this, right? But remember, it will be a case of pure rotation about point A, right? So if there is no translation, if VA become equal to 0, and if it is a pure rotation case about point A, then in that case, that point A, it can be called as instantaneous center of zero velocity. Instantaneous center of zero velocity. And it is represented in short as IC. Now here the word instantaneous, it came out from instant, means at that specific instant velocity will be 0, at that specific instant, right? So means as I have told you, that the word instantaneous indicate that at point A only, that point A is having 0 velocity at that specific instant, and at this instant alone it can be considered as the center of rotation. And based on this, we can identify the instantaneous center of 0 velocity for a rigid body at a given instant. So if we identify, then at that point the general plane motion reduces to pure rotation. So means translation is removed and we are having pure rotation. So this case is a lot easier, means to calculate in term, means for our numerical problems, right? So initially we were having general plane motion, which was a combination of rotation plus translation. So if we identify the instantaneous center of 0 velocity, this means the translation term is removed and we are having case of pure rotation. And in case of pure rotation, the calculation is easy. Okay. So how we can identify the instantaneous center of zero velocity? So sometimes it's very much easy. It can be just identified through observation. Just by observing the system, you can identify the instantaneous center of zero velocity. But in some cases, if it is not obvious, then the question arises that how we can find. But let's have go through this example, and then we will discuss that how we can find it out. Okay. So what they're asking here, if the wheel is rolling without slippage, if there is no slippage, with the shown angular velocity and acceleration, this is angular velocity, this is angular velocity, this one is angular acceleration, determine the linear velocity and acceleration of its center point G. Linear velocity and acceleration of this point, center, right? So if there is no slippage between this wheel and this surface, then at this instant, the point where this wheel make contact with the ground, so if there is no slippage, this means the velocity of this wheel and this ground at this point should be same, and we know that the velocity of ground is 0. So if the velocity at this point is 0, that can be basically the instantaneous center of zero velocity. At that specific instant, at that specific point, the velocity is 0. So I have mentioned over here that as wheel is rolling without slippage, therefore the point of contact with the ground should have the same velocity of the ground, which is basically 0. Therefore, this contacting point is our instantaneous center of zero velocity. So the general plane motion of this wheel can now be reduced to a pure rotation about this point only and at this instant. So this is our instantaneous center because the velocity over here is 0. So what we were asked for, we were asked to find out the linear velocity and acceleration of this point G. So we need to have our position vector. This position vector from IC to G, right? Okay, and the rotation is like this. The rotation is like this. So the velocity over here, definitely the velocity will be perpendicular to this position vector. The velocity direction will be like this, right? So this is the position vector, means the position of point G with respect to instantaneous center of zero velocity, and it can be given as RG, position of point G with respect to instantaneous center, right? Okay, and we know that the velocity will be perpendicular to the position vector, which we have shown over here. Okay, so if you want to find out the linear velocity of point G, since we are having simple rotation, so that will be cross product of angular velocity into the position vector. And since the rotation is like this, the direction, it will be perpendicular to the plane. This is xy, so direction will be perpendicular to the plane. And if this is plus z, so the unit vector along z is k. So that's why we can write this omega k. Okay, and this direction of position vector, it is along y-axis, and it is along positive y-axis. So Rg by Ic, instead of this we can write as Rj. So when you take cross product of k and j, what you basically get, you get minus r omega, and k cross j will give us means r will remain at its place, omega will remain at its place, and k cross j will give us minus I. So we get this thing. Now if you want to find out the linear acceleration of point G, so we know that acceleration is basically time derivative of velocity at that specific instant. Okay, and we know that linear velocity is equal to r omega, right? R will remain constant. As you can see, the value of r is not changing. So take that r outside and d omega by dt, and we know that the time derivative of angular velocity will give us angular acceleration. So instead of this one, what we can do, we can put alpha. So we get this value minus r alpha I. So this is basically the linear velocity, and this is basically the linear acceleration of that point G. Okay, as I have told you that if it is obvious, then sometimes we can find out the instantaneous center just by observation. But if it is not that much clear, then how we can find out, or how to find out instantaneous center of zero velocity? So there are certain conditions, the two conditions that we have. Let's discuss. The velocity is perpendicular to relative position vector. Means if we have this object and we have this velocity, for example, if this is point, so this is the position vector, the velocity is always perpendicular to it, right? Means if this is the object and this is the point where we want to find out the velocity, and this is the position vector, so the velocity at any instant, it will be perpendicular. This is first case, right? Then the velocity magnitude is proportional to the relative position. Means there is a proportion between this velocity and this position vector. This means if it is increasing, this one will also increase, something like that. Okay, let's discuss different cases. So this is one of the case. So in this case, as I have told you, that velocity is always perpendicular to the position vector, relative position vector. So perpendicular is like this, and in this case, it will be like this if you want to make it perpendicular. So when you extend this one, they intersect at a common point, and this is basically the instantaneous center, like this one, as you can see over here. So this is the instantaneous center. So from instantaneous center, you can find out the position of A, and you can find out the position of B, right? So this is the position of A with respect to instantaneous center. This is the position of B with respect to instantaneous center. So just by using this first one, we can find out the instantaneous center in this case. Now let's consider the second case. If both velocity are in the same direction, in previous cases, both velocity were in different direction. Now, if both velocity are in the same direction, means if both of them are parallel, but their magnitude are not equal, right? So now in this case, if you draw perpendicular line, definitely instantaneous center will be somewhere over here on it, but we don't know where it can be. So we can use the second. The velocity magnitude is proportional to the relative distance. The velocity magnitude is proportional to the relative distance. So what we can do, we can draw a line that basically join this one, and we will extend it, and the point where it meets, that will be our instantaneous center, like this one, like this one. So this is our instantaneous center, and you show here we are having the proportion. The velocity VA, it is proportional to the position vector RA by IC, and the velocity B over here is more, so the position vector is also having greater value, that is RB by C and VB both are having bigger values than VA. So if you are having case in which the velocities are parallel in different magnitude, so you can use the second option. So this is the instantaneous position, instantaneous center of zero velocity, and if you want to find out the position of point A with respect to this one, so it can be given as RA with respect to IC, and the second one with the green color, this will be RB, the position vector of point B with respect to instantaneous center. Now we are having case C, in which both velocities are basically parallel, both are parallel but opposite direction. So again, we need to draw that perpendicular line. We need to draw that perpendicular line. Definitely the instantaneous center will be somewhere between them. Join both these velocities, and the point where it intersect, that will be basically instantaneous center. Again, the second option, the second comment, that is the velocity magnitude is proportional, can be used over here. That is the position vector, it is proportional to the velocity vector. Similarly over here, position vector is proportional to the velocity vector. So what RA is showing, RA by IC, that is the position vector showing the position of point A with respect to instantaneous center. And similarly, RB by IC showing the position of point B with respect to instantaneous center. So these are all three cases. Okay, so here we are having a general equation from which we can write for this diagram that if you want to find out the velocity of point A with respect to or about, if you want to find out the velocity of point A and definitely with respect to instantaneous center, so its ratio with the position vector about point IC, that should be equal to omega, means the angular velocity of this rigid body. Similarly, if you want to find out the linear velocity VB with respect to IC, so its ratio with the position vector about instantaneous center, this should also be equal to omega. So you see, this is equal to omega, this is also equal to omega. Now let's have an example on it. The same example, but this time we want to solve it with the new method. You want to solve it with by using instantaneous center of zero velocity or by utilizing instantaneous center of zero velocity. So if collar C slides with linear velocity as shown, determine the angular velocity of rod BC at instant shown. Okay. So first we need to analyze this diagram. Let's see. This point is moving towards the right, and it is possible only if the rotation is like this, right? So if this is rotating like this means it will also rotate like this. So the velocity of point this, it will be perpendicular to the position vector. Definitely position vector will be like this. Okay, this is VB, and if this is VB and this is the velocity, so draw a perpendicular line to it. Let me draw it again. Okay, let's change the color of pen. Okay, if I draw line like this and perpendicular to this one will be like this, right? So the point where it intersects here and here it intersects, so this one will be our instantaneous center. So the position vector of V with respect to instantaneous center, let it be RB by, not RB by A. This one is showing by this red line, and this is B, this is C, so it can be RB by C, and it is already given as 0.6 meter. And if you want to find out its components, so you can find out its component. This component will be 0.6 cos 60, 0.6 sin 60. Okay, and if you want to find out the position of this point C with respect to IC, that is instantaneous center, so we need another position vector which is given here, that is RC with respect to instantaneous center, right? Okay, so if I complete this one, so what we get, we can get a triangle over here. So in this triangle we are having this value 0.6, we have this value 0.4, 0.6, and this is 0.4, 0.4, 0.6. Okay, this angle is 45, so this means this angle is also 45, so this one will be also 45. So this one 45, and if this one is 60, this one should be 30. So this is 30. This one is 30. So 45, 30, by solving, you subtract these two from 180, you will get this one as 105. So by using sine law, This is 0.4, this is 0.6, this is 105 degree, this is 45, this is 30. This one is only unknown. So by using sine law, RC by instantaneous center, that divided by the corresponding sine of angle 105, that should be equal to 0.4 divided by sine 30. From here you find out RC by IC, which is 0.773. And thus by using this equation, for example, VA by RA with respect to instantaneous center, that basically gives us the angular velocity. Okay, we see divided by the position vector with respect to instantaneous center, that will gives us the angular velocity, right? So by doing so, by putting the value of VC, which is given over here, and also RC by IC, which we identified from there, by putting these value, we can find out the angular velocity, which is given over here. So if the color C slides with a linear velocity as shown, determine the angular velocity of rod BC. So the angular velocity of rod BC has been identified. Okay. So again, this is a brainstorming question for you. You just need to go through it, you need to solve it, and then you need to compare the answer with given options, and you need to select the one that closely resemble your final answer. Okay. The problem that you need to go through, you have to do related problems from chapter 16. Maybe you can do 16, 8, and some other related examples. And you need to also go through the related problems from the exercise of your RC Hebler book. And again, remember, this is chapter 16. Okay. Thank you. This is the end of lecture. If you are having any question, you can ask. If there is no question, let me know so that I can put recording off. Or if you want to discuss anything after putting the recording off, let me know. Ji, is it clear to everyone?
Yes, sir.
Should I put recording off?
Yes, sir.